So today's probably the most conceptual day that we're going to have because we're going to talk about files, we're going to talk about mutable state, and we're going to have to talk about resources. So the first concept is this thing called state, or sometimes called program state. And we're going to define this as the sum total of all a program's input data and all the code that acts upon this data. So maybe you remember from like when you took i210, maybe someone drew you this kind of conceptual picture that said that a program involves some input. After it gets some input, it does a little bit of processing. And then after some processing, it does some output. The sum total of this entire thing can be thought of as a series of states. So we can talk about the output state, and the output state is probably dependent on maybe a few things that happen between things in the program. So maybe you get some input, then that happens, then this happens, and then either this thing happens or this thing happens. The total is called the state of a program, and each of these things along the way is some kind of intermediate state. I'll just say intermediate state right there. So if we take a moment to just maybe concentrate on the variables, we say that there's parts of a program that can come in two flavors. We can say that either a variable is immutable, in the case where a variable is defined and never updated. Sometimes immutable is also called, called constant, so constant data. The other situation is that if an object in the language may be updated over time, then we say that the programmer mutated the state of objects in the program. So let's see some examples of this. Like, let's say we start at Python, and we say x equals 1, maybe we say x plus equals 1, repeat that a few different times, and then eventually see what's inside of the x when we're done. Let's give some names to these concepts. So this first step up at the top is called initialization, or sometimes just called init for short. Each of these individual steps along the way is mutating the state of that variable to produce some new intermediate state of x. So in other words, we say that x is a mutable variable. So why does this really matter? Well, mutability is one of these really powerful facts about the language, but mutability also provides a kind of a barrier to understanding and reasoning about how the program should work. So the other way that we can think about this is that since we are programming in this Unix-like operating system, there's actually something else that behaves really similar to variables, which is we're also running Python. So we're running Python on a Unix-like operating system, which itself is a giant blob of mutable disk space. In other words, files kind of act like the variables here. Whenever Python is interacting with the operating system, such as reading the files or writing to the files, we're inherently dealing with some mutable state. So let's quit out of Python with Control-D. Let's maybe imagine that we have some new file right here, such as demo.txt. What if we cat out demo.txt? Well, there's nothing inside of it, but if we were to edit nano, maybe put something inside of it, close it out, then we changed the value inside of demo.txt. So notice this right here is actually really similar to those steps that we talked about up here. We initialize a file with touch, we modify or mutate the contents of that file with nano, and then similar to the way that we looked inside of x to see that x now contains 7, we can look inside of demo.txt after modifying it in order to see what the new contents are. So with those out of the way, let's do a little bit of cleanup. I'm going to remove this demo.txt, and then my next goal is that I want to figure out where am I going to work for today. So inside of i211, I have a Hazel i211 starter that I'm going to be working on, and I'm going to open that up in Visual Studio Code. Once Visual Studio Code is open, I don't think I'm going to need this anymore because I'll work in kind of the integrated terminal with Visual Studio Code for a little bit. Maybe I'll get my bearings as to where things are inside of my file system. That's right, so I have a notes directory. So let me go ahead and open up an integrated terminal, make that a little bit bigger, and figure out where I am. So let's close that out. Let's see. Let's maybe make the terminal just a tiny bit bigger so that we can see. I'm going to cd into my notes. Okay, so we have some stuff for lesson 5. let's just kind of keep this pattern going. So let's create a file called lesson06.py. Okay, now Control P to open my mini view. Let's do lesson06.py, and I'll work in here for a little bit. So print lesson 6. Let's see if that's working okay. Python 3 lesson06.py. There we go. Okay, so we have a couple of kind of vocabulary points that we want to talk about first. So this first idea, which is stateless programs, is kind of a way that we've really been thinking about a lot of the programs that maybe we wrote to get us started in 211. So we have a program right here that says lesson 6 inside of it, and let's ask kind of maybe a question that almost seems like too obvious to even ask. So when I run lesson06.py, how likely, so you have two options. Do you think, door A, that this is going to output the string lesson06, or do you think this is going to output the word fish? Okay, you have two choices. Is this going to output lesson 6, or is this going to output the word fish? I always say the great thing about computers is we can find out. So that output the word lesson 6 and not the word fish. Why? Well, we know that this is the case because, well, we can look inside of the data, inside of the file. And the reason that we want to bring up this idea of stateless programs is that there is nothing else inside of the file. So all information about the program, so all behavior about this program is defined inside of the program itself. In other words, we say that the file is independent, or it has no dependencies on any outside data. We have a file, and there is nothing else that this file depends on. Therefore, we can be pretty certain about what this is going to behave like. So this may seem like overly simple, but the nice thing about this idea of stateless programs is that they tend to be really easy to reason about, and they tend to be really easy to test. The downside, though, is that the real world tends to involve like reading or incorporating data from the outside world in it. If you have a program that is stateless, you can't really react to anything. Everything has to be defined up front in order to reason about it. So let's kind of move on. So if you have stateless programs, what is the opposite of a stateless program? Well, the opposite is a stateful program, something that is potentially incorporating outside information into its behavior. And we've actually seen a few different versions of this already. So the first narrow form of statefulness that you might have seen was when we were writing programs that included random behavior. So let's kind of contrast this very simple program where we just print something out with this other example where we import the random module and then we print out the result of calling random.choice A or B. So maybe if you don't quite remember what this does, this is just going to select either A or it's going to select B. So here's a new question for the audience. Which will it select, A or B? Think about that for just a moment. So here's the weird part. You probably know that it's going to be one or the other, but the output is, of course, random. So we really can't know what it's going to be until we actually run the code. So maybe I can run this 1, 2, 3, 4. Okay, bad example, bad example. Okay. There were quite a few A's in a row, but sure enough, there was a B that happened eventually. So I don't want to get too deep into exactly like the nature of randomness or how randomness is actually implemented inside of computers, but I do instead want you to think that the reason that randomness is possible is actually because of state, Why? Okay, so why is this the case? So what is it that is actually causing Python to randomly choose between A and B? Well, randomness has something inside of it that is keeping track of state and somehow like causing it to change from one state or another. So when we launched the Python interpreter, something happened in the background which figured out whether or not A or B should happen. The exact nature of this is stuff you can read a little bit further. It's all about like pseudo-random number generation and like Mercian twister internal state handling. But at a high level, there is something inside of random that we can't actually control, which is something called the seed value. So what if I just put in like 1, 2, 3, 4, 5 right here? And for all of you Minecraft fans, maybe you've even heard of this term before, such as picking the random seed for world generation. So the seed actually comes up quite a bit in like any pseudo-random number generation stuff. But the process of us saying random.seed here actually causes random to no longer behave randomly. So previously, when we were calling this random.choice, something was happening in the background where Python was picking numbers at random. But now, if we run this, okay, well, I just see the letter B over and over and over again. So what if I do like, let's see, while true do python 3 lesson06.py done. Okay, so I'm going to run this in a while loop, and no matter how many times, so it's still running, it's still running, it's still running, there's a while loop happening, and no matter how many times we run python 3 lesson06.py, it is always going to pick B. And it's always going to pick B because we've set a seed value right here, which is causing a change in how random behaves, and therefore makes this behave as if it were constant, or as if it were stateless. So we can kind of think of these as a series of boxes. If we modify random.seed, that causes something to happen, which makes random.choice deterministic, which therefore makes the entire program deterministic. So we can think of there as being a series of cause and effect relationships between the actions we take and the results we see out in the world. The takeaway then is that random is actually stateful, but maybe it's stateful in a way that we don't 100% quite understand. The other idea is that statefulness is actually sometimes hidden from us. Sometimes there's some kind of behind the scenes behavior which is really explaining how things really work. And maybe if you take this a step further, sometimes this idea of statefulness needs an escape hatch. So sometimes there is a way where random, in this case, maintains some internal state, but in order to make things more deterministic or allow us to control the randomness in some way, there is a way that we can kind of act upon that statefulness in order to make it behave a little bit more consistently. What's the last point? So the last point is that the stateful programs that are usually really useful are those that are actually using system resources or are interacting with the user in some way. So we have to acknowledge something, that programs run on computers, which in turn have a limited set of resources. So a resource or a system resource is kind of just anything that's on the operating system. So files, for example, are a resource. The directories that we put those files inside of our resources, and really quite a few other pieces. So one way that, let's get some practice with this, is let's do 2 different files. So let's say we have, and I'll just kind of follow along with this. So sumfile.txt and fileconsumer.py inside of this directory. So I'll close out of lesson 06. I will open up fileconsumer.py, and I will open up sumfile.txt. Okay, so now I have sumfile.txt. Maybe I'll do that another way, drag it kind of down here so it's a little bit easier to see. Okay, so inside of file consumer, I want to do something like with open the sum-file.txt file in read mode as fh, and I will just print out the result of calling fh.read. So at the moment, we have nothing inside of sumfile.txt, but what would happen if we were to now run fileconsumer.py? Make a guess real quick. There's nothing inside of sumfile.txt. Here we are loading the contents of that file and printing it out. So make a guess real quick. What do you think is going to happen? 3, 2, 1. Yeah, we didn't see anything. If you want to be real pedantic, we did see a new line right here, but it's a little bit beyond the scope of what really matters for this conversation. Okay, but what if we modify the file and say hottogo? Okay, so we put something inside of sumfile.txt. What do you think is going to happen now if we run some fileconsumer.py? 3, 2, 1, make your guesses right here. Okay, cool. So we see hottogo. Okay, cool. So here's the idea. In one of the cases previously, we could notice that we could modify something which caused a change in the behavior of something else, which caused a change in the observable behavior of the random choice.py. Here, we have another dependency, but now it's between the state of a file, or the contents of a file, and the output that we see in fileconsumer.py. So if we maybe add a few more lines to some file.txt, well, hold on, let me do that again in slow motion. So we have some file.txt. I'm going to Control-A to copy everything, Control-V, Control-V, Control-V to paste a few times. So now we have modified that file. And notice also in Visual Studio Code, there's this little period or maybe dot icon right here, which represents that I have some unsaved changes. But if I were to Control-S and save that, Visual Studio Code changes the dot back to an X, indicating that I have nothing left to save. And then if I do Python 3 fileconsumer.py, now we see something different in the terminal. Okay, so what is the point of this? So if we the initialization that we saw earlier was that programs like Touch will create an empty file by default. And the first time we run our script, we may see that there's not really anything inside of it. So actually, let me modify this a little bit just to make it real consistent with what's happening on the screen. Maybe we remove, no, I won't do that yet. Let's do Python 3 fileconsumer.py. Therefore, there are 40 characters inside of this. If we modify the file, add some other stuff inside of this, now we have even more. If we remove everything, then we have 0, etc. Okay, so there's some behavior, though, that we can't necessarily represent just with the code that we've written so far, which is what would happen if we have a situation where we start with some file.txt existing. What is going to happen if we actually remove some file.txt? Python 3, let's do fileconsumer.py, and I want you to think about what do you think is going to happen next? Okay, so we called this thing right here, the fact that we have some file.txt, and the behavior of our program depends on the contents of some file.txt. What do we think is going to happen if we try to open up some file.txt and read its contents and then calculate the length of those contents? Maybe I'll kind of throw out a couple ideas. Maybe the program is going to crash. Maybe the program is going to print 0, like the length of a file that doesn't exist, like maybe that's 0. Maybe it kind of makes sense that that's a 0. What do you think is going to happen in this case? Okay, well, we can find out. Great thing about computers is we can just kind of hit enter and things just keep happening. And ooh, we got a traceback. So let's kind of zoom in on some of this information. So we got a file not found error that indicates that there is no such file or directory, some file.txt. And I actually want to parallel something else as well, which is we've spent quite a bit of time talking about some of these like basic command line programs such as cat. What do you think cat does when we cat out some file.txt? Do you think it's going to behave similar or different to how Python is behaving? Okay, well, cat, it doesn't quite give us all of this information where it's giving us a traceback as to where in the program something broke, but it does give us something very similar in terms of like some file.txt, no such file or directory. So let's actually parallel those last couple points. No such file or directory, some file.txt, no such file or directory, some file.txt. Same information, different order. As a side note, I actually have my shell set up to show this one thing. We could actually look at that in another way, just as kind of a nice way to represent it. So this thing right here, this $? is called an environment variable. And what it represents is the state of the previous command. I feel like state is about to turn into like the word of the day for this lesson. So the previous command that we ran, cat, had an error. Therefore, the $environment variable, $variable returned a 1. In Unix speak, there's a few different ways that these can tend to end. Usually these things are called like exit statuses, return values, error codes, exit codes, etc. By default, a 0 exit code usually means success. A 1 typically means an error, and some of the other common ones kind of crop up from time to time as well. So if I did something like ls, well, ls succeeded, therefore it returned a 0 error code. But if I try to cat out some file.txt, which doesn't exist, it will communicate to my operating system that an error occurred, which is through the 1 value, and it also communicated some information back to me, the programmer, that there is no such file or directory called some file.txt. So here's a question that we may want to go next. What is a way that we could modify this file consumer.py in order to make it a little bit more cat-like? In other words, how would we make it so that Python 3 could say like file consumer.py, and instead of getting this like traceback where it's saying like file not found error, no such file or directory, some file.txt, how could we make it behave a little bit closer to cat? Okay. So maybe we can sketch out an idea real quick. What if we could detect, I'm going to use that and it's kind of scare quotes. What if we could detect whether some file.txt exists or not and change program behavior, and change behavior based on that. Try that again. Okay. So I think we have like some concepts that we've seen quite a few times before. So detect. Okay, I don't quite know what detect would be. Change behavior exists or not. So this kind of sounds like the basis of an if statement or some kind of way to conditionally change behavior or change whether we read the file or not. So let's kind of re-explore some other concepts. So in the previous lesson, where we were talking about rock, paper, scissors, we talked about this special thing called standard error. So from sys import standard error, which, let's see, cat some file.txt. It's maybe not necessarily obvious from reading this, but this is one of those like trust me kind of situations. What you're seeing on the screen is actually being appended to that special standard error location. Okay. So we're aware that there's something called standard error. Maybe we're vaguely aware that there's this thing in Python called the operating system or the OS module. So I'll just kind of sketch this out for now. We could say something like from OS path import is file. What is is file? Well, let's find out. Let's take a look. Hover over is file, and it says is file is a function which takes a file descriptor or path and returns a Boolean, which tests whether a path is a regular file. Okay, so how might we use this? Well, let's see if we can say if is file some file.txt. If it is a file, maybe we'll say that we want to actually open this. If it is not a file, maybe we want to print something, such as some-file.txt, no such file or directory, and we're going to send that message to standard error. Okay, I think we might have this. Let's close out of those comments. Now our hunch is that when we run this code, since we can detect now that some file.txt is actually a file, hopefully we will see something in one case, but if it isn't, we will see something else. So now what happens? Python 3 file underscore consumer.py. And sure enough, actually, let me do one other thing. So remember, cat exited with an error code of 1. Currently, we are exiting with an error code of 0, indicating success. So let me do one other thing. Which is say from sys import exit. And I want to also say exit with the error code of 1. Maybe let's confirm. Okay, so I hovered my mouse in Visual Studio Code over the word exit. Exit is a function that we imported from sys. It takes an exit code and it, well, doesn't return anything, but the result of calling this now is that if we do Python 3 file consumer.py, because we were in this branch of the situation where we exited with an exit code of 1, now the result is that information is propagated back to my operating system, which I can then inspect the state of the previous command by doing echo $? So now we are exiting with a status code of 1. Okay, so let's round this discussion out because we've manually tested what happens in this situation or this branch. Now let's test whether or not this thing is also working. So I bet if we touch some file.txt, now that this file does exist, we can cat out some file.txt and get a valid solution. So I bet now if we run our file_consumer.py, we are going to see that the length of this empty file is indeed 0, and we get a 0 return value at the end. Okay, so we've covered quite a bit of ground. Let me do a little bit of cleanup real quick, because I think I do want to hold on to this file consumer. I think this lesson 06 thing is empty right now, so I think I will just go ahead and remove that. And maybe while I'm thinking of it, I'm just going to go ahead and add a couple of these things and maybe say like git commit -m sparkles emoji. Add some notes for lesson 06. Okay, so where do we want to go next? Yeah, so we mostly covered most of this concepts. We implemented some ideas in rock, paper, scissors. This is kind of all walking through the same information. Okay, so let's kind of review some of the topics that come up when we're talking about some of these stateful programs. So especially when we're dealing with these things, which have dependencies to outside resources, we'll say that they are a little harder to reason about because they take in information that is not really stored in the program itself. They can also be a little bit harder to test because we may not be able to enumerate. Well, let me specify this point a little bit better. So here there was this kind of binary outcome. The file either exists, or it does not exist. So here it is fairly reasonable to say that we can enumerate all possible states because either something exists or it doesn't. There's not really a great intermediary case, asterisk next to that, ask me about it sometime else, that is able to represent all the possible inputs. And sometimes it's even harder to set up the tests. So maybe as an exercise to the reader, we're not necessarily going to cover this today, but how might you actually implement something like this as a unit test? Well, as a unit test, you somehow have to think about the situation or even represent something on your operating system where some file does exist versus what the function will behave like when this doesn't exist. Maybe think about that later. Okay, so in spite of these challenges, the majority of what we'll call useful, interesting programs do have some stateful behavior where they are interacting with the operating system or interacting with the user in some way. One of the ways, since we think that they are worth the trouble, is that we incorporate some kind of defensive programming where we try to reason about the things that could occur, guard against bad data, which can cause problematic results, and importantly, we also provide adequate feedback to the user when a problem does occur. So in that case, the defensive programming was this idea of using an if statement to check whether something exists or not, and giving adequate feedback, such as giving information to the user about some file or directory not existing. So, okay, quick concept review. We have 3 programs which illustrated 3 cases. When we have stateful programs, all data and behavior is defined up front, making them fairly easy to reason about. But we also have these stateful programs where we can't necessarily reason about everything. But we also have a lot of stuff in between, which has aspects of stateless behavior and aspects of stateful behavior. So the question that we want to go forward with next is, how do we identify where in a program the state changes, and how do we effectively build these hybrid programs that can safely handle bringing external information into our programs? Hey folks, this is Future Alexander watching back the tape. There were like 45 minutes here that I spent just kind of talking about pure versus impure functions, talking a little bit about Python review. I really think that this is material that is really just as effective if you just kind of read the material in the book. If you do have any questions, I'm happy to chat about this on Discord, but instead I'm going to jump ahead and get into the implementation of the practice problems today. So 3, 2, 1, if you hear the sound of my voice, that means that I'm going to start implementing some of the practice problems just so you have like something that you can refer to later. So let's double check, where am I? What is my status? Yeah, I'm ahead of main by 1, but that's okay. I'm going to go ahead and open up RPS because I think we're pretty much going to be working in here for most of the day. Okay, so question 1, how will we represent the actual game history? And here's kind of a conceptual breakdown. We have a human choice on every iteration. We have a computer choice on every iteration. So what if on the first iteration, we just have the first game? What if on the second iteration we have, so rock, then paper, paper, then paper, maybe on the third game we have scissors and rock. How would we represent this idea, which we show right here in a table, as some kind of file? Well, I'd say the important information is that each of these lines, so this line right here contains some information, this line right here contains some information about a game, this line right here also contains some information about a game. So I bet we could represent this kind of as a simple file where we have rock, then paper on the first line, we have paper, then paper on the second line, we have scissors, then rock on the third line, and we will use maybe just this comma to delimit which one is the human choice and which one is the computer choice. So maybe this isn't the most user-friendly way, but as long as we can kind of conceive of this as being human, computer, then we could look at this file and pretty much have an idea for what the history of the games are. Okay, so step 2, tell Git to ignore the history file. Okay, so we're going to use a gamehistory.txt. So let's add this to the git ignore. A few ways we could do this. Let's just open it up right here, open up the git ignore. I'll just jump to the top and I will paste this in here. So this means that the gamehistory.txt file is not going to be tracked. So let's add your git ignore and commit the changes. Let's do something git status. Let's do git add.gitignore. Git status just to confirm that that is now in the staging area. Let's do git commit-m, give it a emoji. Let's do the see no evil emoji and say add game-history.txt to .gitignore. Cool. What's the next step? Okay. So now let's see. Do we have a game history? Okay, so I'm going to create game-history.txt. Okay, so we now have that, and the gamehistory.txt is currently empty. Okay, so now we want to write a function that opens gamehistory.txt, reads it, and returns a string. Okay, so we want a signature kind of like this inside of RPS. So maybe I'll kind of just do this new section at the top that's dealing with some of the file I/O. I'll leave a little bit of a comment right here. We want to do some functions related to file input output. Okay, so this load game history, well, we know it's going to be dealing with that gamehistory.txt. So let's see, first step is that we want to open that. So let's do with open game-history.txt. Let's specify that we want to do read mode, maybe as fh, file handler, a little bit of a personal preference. And let's just return fh.read. Okay, so let's do some manual testing. So how do we know that we've implemented this? Well, let's find out. Let's print out the result. Print out the result of calling load game history. And this is another trick I like to do. I'm just going to type the word exit right there, which means that we will start executing here at the top. We will run this load game history function, and we will exit immediately to get some real-time feedback. So let's see what happens. Clear the screen. Let's do Python 3 RPS. I'm hoping we get nothing. Yeah, sure enough. Okay, so it looks like we successfully read the contents of gamehistory.txt, but nothing was output, and that's kind of what we expect. I'm going to kind of jump ahead a little bit. I'm going to copy this information, and let's see what happens if I open up game history, paste that inside the text file, maybe hit enter, and close that out. What happens now? Okay, well, I print out the result of opening that file, and it looks like when there is something inside of gamehistory.txt, it pretty much works as expected. Okay, so I'm going to do a tiny bit of cleanup because we've manually tested and we've kind of seen the purpose of this. Let's do git status. Let's do git add. Let's say git status, git commit-m. What step was that? Okay, cool. Let's say something like add load game for step 3 of day 6. Sure, something like that. Okay, so what's my next goal? Okay, so the next goal, parse the game histories. Okay, so write a function that returns the raw string representation. Okay, so that turns the raw string of game histories into something useful, like a list of lists of strings. Ooh, okay. So let's kind of see what this looks like. Okay, so parse game history. We take a string as input and we want to return a nested list of strings. So, okay, so hint, remember to focus on what the data of the function consumes, its inputs, and what data the function produces, its output or return value. Okay, so if history is a string that looks like this, then the output should be a list of strings that looks kind of like this. Oh, wait a minute. What do we notice about this? Huh. Oh, okay. Okay, this is kind of a side note. Let's write a test. Because notice we have a clearly defined input, we have a clearly defined output, and we have these pairs. So if you give me this, I want you to create this. Okay, let's write a unit test for this. I'm going to do some, I'm going to be real professional here. I'm going to be a test-driven developer. Okay, so class, what would this be? Parse game state tests is a test case. Test case. Okay, let's do test rock parsing. Extend self. Okay, self.assert equal. Okay, so what happens if we call RPS? So RPS.parse game history. So if we have an input like this, do we get this as an output? Okay, well, we have a test. So what happens if we call, let's clear the screen, make it a little bit easier to see. What if we do Python 3 test RPS? Okay, well, of course, we currently return none, but we wanted to return this. Okay, so we have a test, and if that test passes, I think we'll accept the solution. Okay, so we have raw. We want to think about like raw is going to be something like rock, new line, rock. Okay, so this is one of those cases that I said kind of looks like it's coming out of a file because it's got this new line on an end and some new lines in between. So let's kind of build up toward a solution. And maybe I'll kind of do a little bit of the best of both worlds where I incorporate the test, but I'll also do kind of this other version down here where I'm also writing some incremental code in between. Okay, so for now, let's kind of do a little bit of both. So we've started writing this function. I'll write something in between here where I can get some real-time feedback. And what happens now when I run, let's maybe make that a little bit smaller so you can see all these things at once. Okay, so now what do you think is going to happen? I bet it's going to say none because that's what we expect. Sure enough, oh, let's print out that result. So Python 3 rps.py, sure enough, there's my none. Okay. So we have to use this raw somewhere. Currently raw is not being accessed, which means that we probably need to do something with it. What's a good step? Well, maybe I don't quite know, but I bet we could do something like print out raw.splitlines, because I bet this has something to do with split lines. Okay, what happens now? Oh, cool. Okay, well, I've made a step in the right direction. I now have a list containing two things, which is a rock. Okay, so this is a single string followed by a single string. Is this passing yet? Well, let's run those tests. Python 3 test rps.py. Oh, wait a minute. We actually exited. Let me drop that out real quick, just as a quick reference point. Okay. So we're still not quite there. Let's also do something like return raw.splitlines. Okay, well, no, because we are currently outputting the string rock, but we want those to be lists. So we currently have a list containing two items, but we want to have a list containing two lists inside of it. Okay, so we have another step that we have to do. We have to convert these intermediate strings into lists. Okay, so I think we're on to something. We can't necessarily just return raw.splitlines, but what if we iterate over these intermediate examples that we're ending up with? So maybe I don't quite know what to do yet, so I'll just do like for line in raw.splitlines, and I'll just print out line. Sure, maybe I'll do something like that. What does this code do now? Up arrow a couple times. What happens if I do rps.p? Oh, well, let me bring these two things back in so that it's a little bit closer to what I expect. So notice I just brought these two things back in. What happens when I do rps.py now? Okay, we're getting somewhere. So on the first line, we had rock, comma, rock. The second line, we had rock, comma, rock, but we're still returning the same thing at the end. Here's an idea. I bet we need to somehow split on the comma. So instead of printing line, what if we do line.split on the comma? What happens now? Ooh, we're getting very close. Okay, so we called line.split, which split that into a list containing 2 items. So we are very close. We currently have 2 individual cases like this, but we want to put those back in a list at the end. So we have 2 things. We want to put this thing right here, and we want to put the second thing right here. How do we put something inside of a list? Okay, hold on. Here's the final trick. Okay, so let's say we initialize like an empty list called out. Okay, so we initialize out to be something, and then instead of just printing stuff, what if we call out.append with the line.split on the comma delimiter? Okay, and then what if at the end of the for loop, let's just print out for now. Okay, what happens when we do rps.py? Oh, we basically have it. But notice that we are just printing it, but we're still returning raw.split lines. Let's do that very last step where instead of returning raw.split lines, we return raw out. Let's kind of tidy up our code real quick. Let's remove this stuff. And I promised you a second ago that we wrote some tests, and if that test passes, we're going to accept this as a solution. Python 3 test rps.py. Yeah, we ran 8 tests, and every single one of those tests passed. Okay, let's do git status. Let's do this as git add everything, git status. So now we have tests and rps.py in our staging area. Let's do git commit -m, sparkles emoji, add test and implementation of parse game history. Cool. Okay, what's our next step? Okay, so let's do a quick review. We loaded game history, we parsed the game history. The next step, let's write a function to save the history. Save the history, where history is a list of strings. Where have we seen that before? Oh, wait a minute. Here is a list of strings. So here's a way to think about this. We have save game history, which kind of does the opposite of parse game history. So parse game history takes a string and it ends up with a list of strings, kind of like this. Whereas this save game history takes a list of strings and returns none. Why does it return none? Oh, okay. Well, we want to write the function to save history by overwriting gamehistory.txt. This requires, again, opening the file, iterating through every game in the history, and writing each game to the open file. Okay. So there's a few steps right here. Let's kind of build up the concepts one by one. So again, how might I actually start making progress on this? Well, this isn't really something that it's not a very easy one to test maybe, so I'm not going to worry about unit tests for a second, but that's okay because I said a second ago the history is going to look something like this. So let's start writing some code that will maybe help us understand whether our stuff is correct. So let's say like hist equals that, and what is going to happen if we call save game history with this history variable? Okay. Well, maybe I don't quite know what I'm doing yet, so that's okay, because it looks like, according to Pylance, history is not accessed, so I bet that means that we probably need to do something with history. So what happens if I just run this code like this? So Python 3 rps.py. Okay, well, we printed out the history. Now here's the next problem. So we want to first open a file, then we want to iterate through each game in the history and write each of those games to the open file. Okay, so what does that look like? Well, we need to open the file, so it's probably going to look something like this. So I'm gonna just be very straightforward. I'm just gonna copy that, paste it right here, fix my indentation. So we're saving, so we need to change the read to a write. So I've changed this to write, and now we can no longer call fh.read. Now we have to call fh.write. Okay, what do I write? Okay, I'm kind of uncertain right here. Well, I'm not using the history, So maybe there's another hint. So opening the file, iterating. Ooh, iterating. That's something I can do something with. So iterating means for loop, right? So what if we say for game in history? Okay, so for game in history, and instead of returning fh.write, what if I call fh.write game? Yeah, okay. I bet this is going to work. Okay, so I have a hunch. I have an implementation. What's going to happen if I run this code? Python 3 rps.py. Uh-oh. Oh no. Panic. I got a type error. Write argument must be a string, not a list. Oh, wait a minute. Okay, Okay, so what is this game? Game is actually a list of strings. Game is a list of strings. Ooh, okay, so we have one observation. At the moment, game, let's see, game is a list of strings. We need to write a string to the file. Okay, so something's not quite right with that. We need to modify that a little bit. I'm also going to clue you into something else, which notice that we crashed. So we crashed when we tried to call this function. So what do you think is going to be inside of gamehistory.txt? Uh-oh. Wait a minute. Where is all my data? Uh-oh. Why is there nothing inside of gamehistory.txt at the moment? Okay, so this is something to be kind of mindful of. If something breaks in the middle of trying to write a file, it actually kind of erases all the contents. So let's kind of see a couple ways that we could think about this. So in this case, it's pretty easy for me to recover this. I can just copy it from here. I can paste it back in there. But okay, so I've put something back in gamehistory.txt. So what's going to happen if I run it again? It crashed last time, and that basically meant that it looks like it erased this. Let's see if we can reproduce that behavior and confirm that. So we call rps.py, it raised the type error again, that cleared out type, that gamehistory.txt. Okay, so this is one of those lessons where it's kind of like, how do we be pretty careful about like, how do we manage our files? Because what did we say earlier? Files are mutable disk space. Because a file is mutable, whenever we open a file in write mode, that potentially means that it will remove anything that was previously in the file. Okay, so there is a little bit of a trick that VS Code will help us with, which, do you see how I have this open right here? What if I go back, I copy this, drop it back in there, save it up. Now what happens if I call rps.py one more time? Okay, well, it did delete that. You could actually kind of see it in real time. I'm going to use a trick, and I'm going to do Control-Z. Okay, so Control-Z is going to bring that back for me. Maybe kind of keep that in your back pocket because that might get you out of some problems later. I'm going to push this to the side for just a moment. Okay, and back to this problem. Game is a list of strings, but we need to write a string to the file. Okay, so we need to first convert this list of strings into strings. How do we convert a list of strings into strings? Okay, well, we're working with an individual piece of data right here. So I think there's there's actually a much easier way, which is that we said that the first thing is the human choice, the second thing is the computer choice. So we can apply an unpacking operation and say that human, comma, computer equals game. Okay, and then instead of doing that, what if we do, okay, so let's kind of write some incremental progress right here. What happens if we print human? What if we print computer? Maybe just write the empty string for a second because we know we're gonna have to put a string in there eventually. Let's put in human right there. Okay, so Python 3 rps.py. Keep an eye on what's happening over here alongside what is going to be printed out and what is the relationship between the fh.write and what's going to end up over here in just a second. 3, 2, 1, go. Oh, okay, so that gave us some information. It printed out the right information. So line 25, the fact that we got rock inside of the console is a pretty good sign. But write, what happened there? Why did we end up with rock? Okay, well, we only wrote the human's choice, but we also did not add new lines between each of those. So we need to correct a couple things. we need to write the human, we need to write a comma, and we need to write the computer, and we need to write a new line at the end. Human, comma, computer, new line. Okay, human, comma, computer, new line. Let's adjust our code. So we probably don't need this print statement anymore. We need to write human plus comma plus computer plus new line is what we said. I think we might have this solved. Let's see what happens when we run this one more time. Python RPS, and it looks like we have a working solution. Okay, that took a second. Let's see if now we can put some of these pieces together. So let me do this one more time. We copy all of this information, and I actually want to see if I can read this game history in and write it back out. So let's do, maybe instead of having a specific history, what if we load the game history? So we say hist equals, or raw history equals load game history. What if we parse the game history, which remember is going to return this list of strings. So the history equals parse game history with the raw history as an input. And finally, what if we call save game history using that history? Okay. So if everything has worked so far, we are actually going to get exactly the same thing. So it's going to look like nothing happened just yet. Let's see if that's the case. So scroll down a tiny bit. I bet now that we've changed it, we're not going to see anything when we actually run this code. So rps.py. Yeah, do you see it? So we ran the code. It doesn't look like anything changed, and that's because we loaded, we parsed, and then we saved the exact same thing that we had a second ago. Let's do one other variation on this, which is kind of getting ahead of ourselves, but that's okay. So what if we append a new observation to the history where we see paper, paper? I bet now the result is that after we see all this, we're going to start seeing new things get added. And this is actually going to modify things every time we run the code. So if we run RPS, oh, cool. Okay, so every time we run the code, we see something new showing up inside of the file. Okay, cool. I'm going to delete those rows because they don't really matter. Okay, I think this is enough to be certain that we basically have the implementation done. So I'm going to put this on my clipboard. I'm going to exit out of this. I'm going to see if I can make a commit here. So let's do git status, git add rps.py, git status one more time. It's in my staging area, git commit-m, sparkles emoji. There we go. Implement saving. There we go. Okay, so what's my next step? We just implemented saving. Okay, so now is the crux. Update the history every time we play a game. So we want to use our load game history, our parse game history, and our save game history in order to update this gamehistory.txt file every time we play rock, paper, scissors. Okay, let's do it. Okay, so that's going to be in the main block. So I'm going to scroll down. Okay, so what does this take? Well, we need to use all three of these definitions. And I actually kind of cheated here because notice that it's on my clipboard at the moment. So I'm going to paste that stuff down here. So here's where we're really dealing with update the game history on every play. This one might actually be okay as a comment. So the first thing I'm going to do is I'm going to load the raw history. I'm going to pull in the history. Okay, but wait a minute. Okay, so here's where we parse the game history. So in between parsing the game history and resaving it, I'm going to say history.append, and now is where I'm going to pull out the human and the computer. Okay, we might have it. Okay, so we load, we parse, we update the game history by adding a new observation, and we save that entire history back to the file. Okay, so let's see if that actually works. So we're going to do a manual test right here, Python R3 rps.py. It's going to ask me scissors, paper, rock. I'm going to say rock. Oh, cool. Wait. So I chose rock. The computer chose paper, and now that's reflected. I chose rock, computer chose paper. Let's do that a couple more times, just kind of check that things are working. Python rps.py, rock again, scissors, rock, paper, rock. Oh, cool. So we are updating every time we play the game now. Okay, I think I'm pretty confident in this. We've modified RPS. Let's git add rps.py, git status, git commit-m. Let's see, add or sparkles emoji. let's see, save, or let's see, save data every time we play RPS. Awesome. Okay, what's the next step? Okay, so we did step 6, we played RPS a few times, and yes, RPS, the game history does change every time. Step 7, delete the history file. Ooh, okay, well that's an interesting idea. We could restart the history from a blank slate simply by removing the gamehistory.txt file. Okay, that's an interesting idea. What happens if we, okay, close this out? Maybe I'll even do this in Visual Studio Code. I will right click this file. I will say delete permanently. Windows is going to warn me, hey, you can't restore this. Okay, cool. Let's get rid of the history. We don't need that anymore. Okay, so what happens now? Now that I've deleted the game history, what happens now when I run rps.py? Oh, okay. Well, it's still going to ask me rock. Uh-oh. Ooh, wait a minute. Okay, hold on. We got an error message. So we still were asked, what do we want to choose? It still says that the computer chose scissors, but then we got a trace back. Okay. So what happened? Well, the most useful message in the traceback tends to be this very last line, which says file not found error, no such file or directory, gamehistory.txt. Uh-oh. So we removed gamehistory.txt, and therefore it's not available for us to load the game history. So on line 79, we are now going to cause problems because we can no longer load a game from a file that doesn't exist. Okay, so what do we do? Well, we answered that, we cannot play RPS anymore because we've deleted the file. Okay, so step 8, let's handle the missing file case. Earlier we saw this thing called os.path.isFile, which answers whether a file exists or not. So how would we update our code to handle the initial case when the file does not exist? Okay, so we kind of have some choices here. Like what would make sense to do if the file doesn't exist? Does it make sense to crash the program and never let the user really play the RPS game without actually seeing this giant warning message right here? Oh, this is terrible. Okay, so what might we do instead? Well, it would be kind of interesting if we could just pull out some default value such that we could load from an empty, like maybe load some information, maybe parse something, maybe, okay, I think we're onto something. So there's kind of a few ways we could approach this, but it's something like we want to represent that what happens if there is no initial value. Well, we could kind of represent this by saying that the initial state is an empty list. How might you do this such that there's an empty list at the beginning? Okay, well, I have a hunch. I bet there's actually a really simple fix, which is to jump up to this load game history, and we said something to the effect of, we now need, so like from os.path import is file. I bet there's actually a really simple solution here, which is to say if not is file game-history.txt. I bet we could just return the empty string right here. Okay, so I bet this is actually going to fix it. Maybe on your own time, kind of figure out exactly what this is doing. But now if I run RPS, if I choose rock, oh, look at that. So now what happened? There is now a gamehistory.txt file right here, which we can cat out gamehistory.txt, and now the initial state is actually correct. So if I choose paper, if I choose paper, if I choose paper, then gamehistory.txt, try it from the left-hand side, gamehistory.txt does now again have all the data along the way. Okay, briefly, the reason this worked is that on the initial thing, when we loaded the game history, since it returned an empty string, the result of parsing was that it initialized that empty list, kind of like we said. It iterated over everything in split lines, but the effect of that was these two lines were basically ignored, meaning that it just returned the empty list at the end, and therefore, the entire program is now fixed because we checked whether or not the file existed and returned an empty string. Okay, So I think we're pretty much good. Let's do maybe git diff, just confirm that that's pretty much exactly what we expect it to have. Let's add rps.py, git status, confirm it's in the staging area, git commit-m, sparkles emoji, handle the initial case where game history.txt, game history, if I can spell, .txt does not exist. Cool. Okay, tidy up, commit, and push. Let's do that very last step, git push. Cool, so that should be everything for today.